Okay, this example is 9.3. Change of base formula and solving logarithmic equations. Now, the change of base formula is going to be really pretty easy, but you need to understand what it's used for, and it tells you right up here at the top that your calculators will calculate logs for you, but your calculators are only capable of evaluating logs with a base 10, and that would be if you hit the log button, regular log button, or a base E, and that would be if you hit the LN button, a natural log button. So if you have another base other than 10 or E, then you have to manipulate your calculator to be able to work and calculate that for you. Otherwise, you'd be having to guess and check, and we're not going to be doing that. So there is no direct, since there is no direct way to find a logarithm with a base other than 10 or E, then we're going to use the change of base formula. And that's going to basically translate it a different base into a base that we can use on our calculator. So that formula is this. So you have log base B of M. Then what you can do is change that to your base 10 log by dividing log M by log B. So how has that changed the base? It changed from a B into a what? 10. And since I changed the base from a B into a 10, now I can do it in my calculator. So let's do these common logarithms, or let's evaluate using common logarithms so then we can use our calculator. So how would I write this log base 7 of 5? Okay, good. Log 5 divided by log 7. And so let's evaluate that. Let's go put that into our calculator. So on our calculator, man, it makes that writing go away. So on our calculator, that's going to put it as log 5. So I'm going to put log 5 divided. You need to make sure that you close this parentheses when you put that log 5 in there. So log 5, close that parentheses, divide it by log 7. And there you go. So I want us to be accurate. Since this is, the more places you're going to use, the better, the more accurate you're going to be, and I want us to do this to 4 decimal places. I know in our answers, our final answers, typically we go to 2 decimal places, but since it's an exponent, and exponents change dramatically and drastically, we want to do 4 places. So that means that log 5 over log 7 is 0.8271. Now, what is that really saying? What does that number 0.8271 mean? Okay, sorta. I heard kind of that in there. So that's, if you say 7 to the 0.8271 power, guess what that should equal? 5. Let's try it. 7 to the, darn it, it cleared it. 7 to the 0.82, is it a 0.8271 power? And look at there. 5. And why is it off a little bit? Yes, it's off a little bit because we rounded. Earlier, I had only listed my exponent to 2 decimal places. We did 0.83, and that wasn't real accurate. That gave me an answer of, when I did 7 to the, well, actually I could just calculate it on there. When I did 7 to the 0.83, see, look at how much less accurate that is, 5.028. So 4 decimal places on our exponents is really what you're going to want to do to be accurate. Okay, so go through those, do those, calculate those logs for B and C, and I'll give you those answers here in a second, but go ahead and run through and calculate that. Okay, so there's those answers that you can evaluate in your calculator. Any questions on that? Okay, the biggest part of this lesson is coming up. It is solving different kinds of equations. So before we start actually talking about how to solve these different kinds of equations, I want to demonstrate to you or show you what kind of types we're talking about. Okay. So the first type is an exponential equation. Why do I call this an exponential equation? Very good. Because the variable is in the exponent. So we're going to be dealing with a type of problem where our variable's in the exponent. Okay? We'll come back and talk about that in a second. The next type of problem, look at this next section. Logarithmic equations. Where are the variables in our logarithmic equation? Our variables are located within the log. So for our logarithmic equation, our variables are located within a log. That's going to be solved different ways. And on your lesson, they're all going to be mixed up. Okay, so you're going to have to keep in mind, okay, which type is this? Where's the unknown? And then how do I approach this? Okay? And then the last type is actually the variable is in your base. Oh, man. I didn't want that to happen. Okay, so the variable is in your base. And that's what we're dealing with in this case. So our variable is right there in the base. But notice, this section actually has all three types. This has our variable in the base. Our variable's in the base. This has our variable located in the exponent. And this has our variable located within the log. Okay, so those are the different kinds that we're about to address now. So let's go back to the first type, which is an exponential equation. Okay, so hey, we're talking exponential equations. That means if I'm thinking of a graph of this thing, what kind of domain am I dealing with if I'm thinking of an exponential equation? My domain for exponential equations is what? Negative infinity to infinity. So are these exponential equations? So any answer is good as long as it's a real number. They should all be. So what I'm getting at is, am I going to have to check for extraneous solutions? Anything will work as long as it's real. So no need to check for extraneous solutions because anything's going to work as long as it's real. Okay, so that's what we're dealing with here. All right, so what I want you to do, I actually don't completely like all these instructions I put on there last year, but what I want you to do is use the property of log to get that exponent down. What property of logs have we talked about that you can use to get that exponent down? Okay, so what property of logs can we use to get that exponent down in front? It's that third one. It's the power property. So watch this. I want you to take the log of both sides. So you're going to put a log, you're going to take the log of both sides. So I just wrote log in front of the left side and log in front of the right side. So in other words, here's what I have. Let me write this out. Log 10 to the 3x equaling log 20. What's the understood base? 10. Okay. So property power says, what can I do with this 3x? Bring it down in front. So I get 3x log 10 equals log 20. Okay, how can I simplify that and solve for x? Okay, I can divide out the log. Now, let's not forget, this is an understood base 10, and that's a 10. Remember this simplifying we just did on our warm-up? Really, in essence, this log 10 is 1. Okay, so but if you had typed it into your calculator, it would have done that for you. So we know that that's really the value 1. So what do I really just have to divide by? 1. 2. Do I hear a 3? Yes, I'm going to divide by this 3. 3 is multiplying x, so divide by 3. Divide by 3. And so I'm going to go to my calculator, and I'm going to type in log 20, close those parentheses, divided by 3. And I don't want to type it in because I'm going to lose everything if I do. So log 20 divided by 3. 0.4337. Good? Okay. So, second one. How are you going to get that variable that is up there in the exponent down? Use the power property of logs. But I don't have logs yet. How do I get logs? Take the logs to both sides. Take the logs to both sides. I'm going to take the logs to both sides. Okay, so I'm going to take the log to both sides. Okay, so we're going to take the log of both sides. Taking the log of both sides allows us to pull this 2x down in front of our log. Okay, now, common question here. Okay, so here's something to be aware of. You know, maybe you think that you can just go divide by log 6 and go divide by log 6, and then maybe you think that your logs cancel out and then you just have 1500 divided by 6. That does not work. This 1500 is attached to this log. Those are not separate things that can detach from each other. They are one component, one item, one problem. Okay, so do not think you can just cancel out the words log. But let me go back here. When you simplify this, why don't you do this in one step and divide by both this 2 and log 6. Divide by the 2 and the log 6, because then you can do 2 steps in 1, which will give you x equals. Now, so I'm going to be dividing by 2 log 6. I do need to address how to put this into your calculator because there is an order of operations issue that you're going to run into. But let me write my answer. The answer you should come up with is 2.0408 because whenever I pull up my calculator, it's going to erase all this stuff. Okay, but let's pull up the calculator and talk about how to put this in there. Okay, so I'm going to try and put, oh, it just came. I'm excited. Okay, but now it's going to go away whenever I need to start typing it in my calculator. So I want to put in here this thing, log 1500 divided by 2 log 6. You have to put parentheses around this bottom, this denominator, when you put this in your calculator. Otherwise, so when you type this in, you're going to get log 1500, close the parentheses, divided by, open a parentheses and put 2 log 6, and then close the other set of parentheses. Otherwise, your calculator would do this. Your calculator would go log 15 divided by 2, and then it would get its answer, and then it would multiply by log 6. So that's why you have to include this to mandate that correct order of operations. So let's do that. Let me actually put this in here. Here we go. Okay, so we got log 1500, close it, divided by. I am mandating that it do 2 times log 6 first. And then divide that, log 1500 by that product. Okay. That is how you get the answer 2 point whatever it was, 0408. All right. Good. So those are the problems of how to get the exponent out, or the variable down out of the exponent. Next, what happens if the variable is within the logarithm? What happens if the variable is within the logarithm? Okay, well guess what? Let's talk domain here. If you remember our graphs of our logarithms, what is happening? We have an asymptote, and so our domains of our logarithms are going, a basic logarithm is going from what? 0 to infinity. So since we have a limited domain, guess what you're going to have? You're going to have extraneous solutions that you have to check for, because if your answer is out here, then it's not real, or it's in the imaginary section.
Oh, okay. So extraneous solutions are like imaginary.
Correct.
Okay, now I get it.
Okay, good. So, let me clear this out. Here we go. So here is the way to get rid of the variable within the log is to rewrite it in exponential form. So watch this. What is the understood base to this first problem?
10.
Okay, so this is saying 10 to the 5th power equals 3x plus 1. See, so you just rearranged it in exponential form, and now where is your variable? It's just a regular old, that's a regular old algebra 1 problem. That you're going to say 100,000 equals 3x plus 1, and then you're going to solve. And you're going to get x is 33,333. You are going to check that. You are going to put that in there and see if log 10,000 or 100,000 is 5. So that's what that would be there. And it is. 10 to what power is 100,000? Okay, so that's all meeting our needs. You know, also, we know that our domain... Okay, never mind. We won't go there. Okay, so, B. Look what's happening. I have two separate logarithms. So I want to... Well, they don't cancel. They are all on one side, so that's good. They're all on one side, so that's good. But look, and it says up here, if I condense them to get one single logarithm, then I can then put it into exponential form. So let's condense it using our properties. So, how does this first term condense? Oh, actually, no, I need to condense them together to make one single log. What does this 2 do? It becomes the x's exponent, so that's x squared. My understood base, by the way, is what? Okay, but because I'm subtracting log 3, what do I do with that 3? Divide by 3, okay. So really that's what I have. That is the left side condensed into one single logarithm, equaling 2. Okay, now what? Yep, so now put it into exponential form. That will get rid of the log, so I'm going to say 10 to the second power. See, that's the understood 10 from right there. 10 to the second power equals x squared over 3. And now I have a quadratic that I can solve. How am I going to solve that? Multiply by 3. Multiply by 3, 300, equaling x squared. Now what? Square root. When you take a square root, you have to account for both the positive and negative roots. And let's simplify that. I want you to leave it in radical form. We just need to practice our radicals continually, or else we go brain dead. Do not type square root of 300 in your calculator and get 17 point whatever. You need to continue to practice your radicals. So, isn't that like 100 times 3, which that 100 comes out as 10 square roots of 3. So, plus or minus 10 square roots of 3. Okay. So, let's think about this. Am I allowed to have a negative 10 square roots of 3 within this log? Why? My domain of log x is from 0 to infinity. It has to be greater than 0, and it's not. So therefore, is my -1 actually going to give me an appropriate solution? No. So really, only the positive one was a solution. So the solution is positive 10 square roots of 3. And like I said, put it in radical form so you don't go brain dead and forget your radicals rules. Okay. What do you think about C? Okay. I could move all my logs on one side. Now they are both logs 7, and that's all I have. That's right. I could go through the whole process for that. Yeah, so, and you say, no. So let's just say, since our bases are the same, remember it's like when we have, it's similar to when we have our like bases. What did we do with our exponents? We just set them equal to each other. So guess what? I can just say, ta-da, x plus 2 equals 2 minus 3x. And I can solve it. And x is 0. Oh, now hold on a second. We need to check that guy, because isn't my domain typically not including 0? But I need to check, because this is 0 plus 2, so what does that really make it? Correct. If the bases are the same, then you can just set those inner terms equal. Okay? So let's fill this in. Let's do a little mental check. Okay, so I'm going to check it, and I'm going to put 0 in right here. And so really that's saying log 7 of 2. Can I do that? I mean, log base 7 of 2. Yeah, that's okay. Well, if I put 0 in here, what's that saying? Log base 7 of 2, because usually 3 times 0 is 0, and okay, and those are equal, so we're all good. So that's checking out. So I checked for extraneous solutions. It wasn't one. 0 is acceptable. Okay, I gotta have to move this up so I have room. I'm gonna clear this. We have so much time. Gosh. Okay. Let's do one problem down here, and then you can do all the rest because they're all good. So here we go. What do you do when you have your x as a base? We're going to isolate the x. We're going to subtract the 4. So it's x to the 3 halves equals 27. And here is the trick for when you have an exponent that is a fraction. You raise each side to its reciprocal power. So I'm going to raise this to the 2/3 power, raise this to the 2/3 power. What's the 3 halves and the 2/3 going to do? Power of a power multiplies, that makes it a 1, so it's x. 27 to the 2/3 is really saying this. Cubic root of 27 squared. And I take the root first. What's the root of 27? Get it smaller before you square it. So the cubic root of 27 is 3, and 3 squared is 9. So the answer is 9. You can have any base, so you don't have to check these. The only ones you have to check is when your solution, your variables in the log. So let me give you your lesson. Okay, so I had to get that one through for a class I was leaving, but let's go back and finish these ones that we did not get done. Okay, so let's go back up here. I believe that we did not get to do C and D. So let's do that. For C, because it's natural log, we know that our base is E. And so that's saying E to the 4th power is 3x plus 5. And so I can calculate e to the 4th power in my calculator as 54.5982. And I do not want you cutting off, you need to keep going with all of your values out here until the very end. And then you can just use basic algebra to solve that. And you get that the x value is 16.5327. I would, of course, want to go up here and double check that. And so since that's going to give us a positive value in there, we're okay extraneously wise. Okay. So here I have two separate logs. I need to condense those in order to solve. So what's going to happen is when I condense those, I'm going to get log of x times x plus 3. And so I'm going to have my very favorite thing in the whole world, quadratic, right here, because I'm going to get log x squared plus 3x equaling 1. And so then I'm going to turn that into an exponential by saying base 10. So 10 to the 1 power equals x squared plus 3x. So I'm then going to take that exponential, or that quadratic, and solve it. So x squared plus 3x minus 10, I brought the 10 over, equaling 0. I'm going to factor this. So my solutions are negative 5 and positive 2. So I need to check these guys out. And I can tell you right now, if I put a negative 5 in there, I cannot have a negative 5 in there. Remember, my domain for my logarithms, my regular just log x, is 0 to infinity. Also, think about what that's saying. That's saying 10 to some power is negative 5. Okay, there isn't an exponent that's going to turn something into a negative 5. So there's a couple different ways of thinking about that. So that one is extraneous, does not work. 2 does. I can put 2 in here and I'm fine. I can put 2 in here and I've got log 5. I'm all good. So let's now go down to these ones down here below that we did not get finished. I like this last section because it kind of puts them all together. It gives you this one type with the fractional exponents. Remember, you have to, once you isolate this, to get rid of that fraction exponent, you need to raise the power to its reciprocal power. And so that x equals, and this is your power, this is your root, so this is 27 cubic root squared. I always like to root it first, that's getting it smaller, so that's 3 squared, which is 9. I do not have to check to see if it's extraneous because I can have any base. Now, well, you know what though? If you think about it, yeah, because I'm having a cubic root, and so I can have a negative inside there, plus the fact that I'm squaring it, so it ends up being okay. All right. So the next one, I'd subtract 2 first. 8x to the 5/3 is 24. Divide by 8 to isolate this variable. And once I have that isolated, I need to raise this to its reciprocal power. Raise both sides to the reciprocal power. So x is going to be 3 to the 3/5. Okay, so, however you want to say that one ends up being actually a decimal answer. It doesn't come out nicely. That one's saying the 5th root of 3, which isn't something normal, cubed. Or you could say 3 cubed and then take the 5th root of that. Since that doesn't come out normal, you got a 5th root. You can leave it in radical, or you can go ahead and decimal that one out. Okay, let me erase this here. Our next one is different. Where is the exponent? Or, I'm sorry, where is the variable? I gave it to you. The variable is located in the exponent. So I have to get it out of the exponent. And what have we learned about how to get it out of the exponent? Take the log, so you can use the properties of logs. Take the log of both sides. Taking the log of both sides means you have this. Log 12 to the x minus 2 equaling log 20. And so, power property of logs tells me I can pull this x minus 2, keep that in parentheses, log 12. And so, in order for me to isolate this x, I'm going to divide out this log 12. I'm going to get rid of that log 12, divide it on the other side. So, x minus 2 equals this. Make sure you put that in your calculator properly. Log 20 divided by log 12. And that is 1.2056. I am almost done, but not complete. Add 2. So x is 3.2056. Okay, so that's finished. And let's do the last one. You have multiple logarithms. They are all on one side. But what should I do with all these guys? I want to combine them and condense them into one single logarithm. So, I know this 3 is the power of the x. I know that because this is subtraction, that I'm dividing by 6. And because this is addition, I am multiplying by 2.4. And that equals 9. So, the way to begin solving this is to say, okay, I haven't understood 10 to the 9th power equals x cubed times 2.4 divided by 6. And this just isn't going to be pretty much any way you look at it. It's going to be huge. Okay, so actually took a look at this a different way, and I think it's going to be much better. So let's rethink this. This log 6 and this log 2.2, those are real actual answers that you can calculate. So what if we did that? What if instead of doing this way and getting all this stuff we're manipulating around, what if we went ahead and determined these values? So let's go back to this. It's okay. I can mess up sometimes. 3 log x minus our log 6, which is 0.778. 125. I went ahead and went out a lot of places. Plus our log 2.4, which is 0.302. 11241. And then, of course, you know, there's different ways to do this. You can combine those together and move that all around. But however it is, you isolate this 3 log x, and you move those other items over, and you end up with your 3 log x equaling 9.3979409. Divide this guy by 3, and so then you have log x equaling 3.13264667. Now you have a much nicer exponential to take care of. 10 to this 3.132, what was that, 6, equals x. Then you can solve that. That is much better. The answer ends up being 1,357.21. Okay, I like that way a lot better. I think you end up having a lot simpler time on that.